I would like to present our research work of effect of the stress state on the adhesive strength of an epoxy-bonded assembly. The aim of this paper is to study the temperature dependence of the adhesive strength of epoxy-bonded aluminum alloy specimens under the tension plus shear stress state, and to describe the obtained experimental results with the use of criteria applicable to predicting the probability of the failure of the assembly under operating conditions. The adhesive strength of specimens made of the aluminum-magnesium-lithium alloy was studied. Epoxy resin was used to bond the specimens. To study the effect of the stress state on adhesive strength, we used specimens with inserts from bonded specimen halves as shown in the picture 1. The testing was performed in a Zwick universal testing machine equipped with the environmental chamber. The modified Arcan specimens were fixed in the machine grips so that the angle between the tension direction and the normal to the joint plane was 0, 22.5, 45, 67.5, and 90 degrees. Picture 2. Separation under the action of normal tensile stresses was implemented at angle equals 0. The shear stress state caused by the action of tangential stresses was implemented at angle equals 90 degrees. And the complex tension plus shear stress state was implemented at intermediate values of angle. The testing was performed at -50 plus 23 and plus 50 degrees S. The force R and the relative displacement of the specimen halves along the loading direction during the testing were varied by a dynamometer and an extensometer complementing the testing machine. When formulating the local fracture criterion, we use the assumption that the value of strain energy density in a selected microvolume including the interface is the driving force for the delamination of the adhesive joint under the force action. To do this, we arbitrarily select a microvolume at the interface which simultaneously belongs to the adhesive and the substrate, the aluminum insert, and contains the interface inside, along which slip and delamination are prohibited. The values of the strain energy density components Wn and Ws in the selected microvolume are calculated by the formula as 1. Table 4 shows the ultimate values of strain energy density Wn asterisk for pure cleavage angle equals 0 and Ws asterisk for pure shear angle equals 90 degrees determined for various testing temperatures. Some graphic interpretations of the Wn and Ws being shown in Figure 5. Under the complex stress state, when cleavage and shear stresses act simultaneously, the correlation of the values of Wn and Ws asterisk at adhesive failure are described by straight lines in Figure 5. The equations of the approximating lines in Figure 5 can be written in as Formula 2. Equation 2 has the meaning of a fracture criterion under the tension plus shear complex stress state for adhesive failure. In the normalized coordinates, the fracture locus has a generalized form in Figure 6. The analysis of the obtained results yields a linear fracture criterion and a fracture locus for the adhesive failure strain energy density, which takes into account the ratio of the elastic properties of the adhesive to those of the substrate. The region bounded by the fracture loci of adhesive strength and ultimate strain energy density determines the conditions for the safe loading of the bonded assembly in terms of the energy and force. Criteria of adhesive failure. The proposed fracture loci can be used preferably simultaneously to estimate the in-service strength and reliability of adhesively bonded assemblies.